Good day. This is AP Calculus Summer Review. I am Mr. McCulley, and this is our last one of the summer, SR10, Sigma Notation. Let's get right to it. Okay, today we're going to be talking about Sigma Notation. We're going to evaluate series in Sigma notation, and we are also going to write series that are in Sigma notation. So a little bit of quick background information and review. I have a few equations that you might want to either jot down or make sure that you keep handy when you're doing the practice problems here. So the sum of a finite arithmetic series, and remember when we say arithmetic series, we're talking about a sequence of terms that has a common difference. So each time you go up for a constant amount. So let's just get a real quick example. I could go 2 and then 5 and then 7. No, that's not right. That ain't gonna work. I get 8 and then 11, and you'll notice that this is an arithmetic series that has a common difference of 3. Each time you go up by 3. The sum of a finite geometric series, and remember that equation right there, it's a little bit more complex, but a geometric series has a common ratio, so each time you go up a term, you multiply by the previous term by a similar value. So starting with 2, let's say I'm going to multiply by 3, so I would have 6, multiply that by 3, and I would get 18, and then multiplying that by 3, 10 times 3 is 30. So 54. And that would be the next term in that one. Okay, so the sum of an infinite geometric series, you can sum up certain specific geometric series, and that is if the common ratio is less than 1. This particular series would not have an infinite sum because its common ratio was 3, and that is definitely bigger than 1, so we can't do that. The general equation for the nth term of an arithmetic sequence. So if I'm trying to find these specific terms in my sequence, I can use this equation. And the d is going to be the common difference. In this one, it was 3. Our first term, a sub 1, would have been 2, and then n is whatever term you're trying to find. And then the general equation for the nth term of a geometric series is given as this. R is that common ratio, n is the nth term in a sub 1. And I guess for all of these, a sub 1 is going to be the first term. S sub n is going to be the sum of the first n terms, and S is just going to be the infinite sum of them all. Okay, so let's talk about a series. A series is the sum of terms in a sequence, which I showed in the last page. Whenever you see this sigma symbol there, it is going to imply a sum. And what you'll see usually is just this part. So you'll see a indexing system. So here's our variable, here's my lower bound, here's my upper bound. So basically, usually they start with 1 or 0, but they can start anywhere. And basically what we're doing is we're taking all of the integers from B to C and plugging them in to whatever expression we have here. So when I say a sub I, I'm talking about the general term at whatever I is at that particular point. So if you look at this thing, we could plug in all of these values up until C, because that's the top. And I suppose I should have started with 1 since I put 1 there, but that's okay. We can move on from that. And so just a couple quick examples of how to do this. Now, if we want to evaluate the following sums, this thing says wherever you see, or for all the values from 1 to 5, what we're going to do is we are going to plug those numbers into this equation. Well, there's no n variable here, so there's nothing to plug into. So this one's actually, usually it's a pretty easy one to calculate, but it usually throws people off because I don't have anything to plug in. Well, if I don't have anything to plug in, it's just a constant. It's just 6 plus 6 plus 6 plus 6 plus 6. Why? Because I have 1 to 5, so I have 5 terms of 6. That thing is just going to be 6 times 5, which is 30. Now this next one, it has a few more terms, and it has an expression that I'm going to plug in for I. So essentially what this says is it says plug all of the counting numbers, all of the integers from 1 to 10 in for I, and calculate them using this equation, and then add those values up. So let's do a few. So if I plug in 1 times 2 is 2, plus 1 is 3. Then I plug in 2. 2 times 2 is 4, plus 1 is 5. I plug in 3. 3 times 2 is 6, plus 1 is 7. And I notice I get a common difference and a common difference. I get 2 and I get 2. So this is an arithmetic, arithmetic. It's an arithmetic series. Now, I don't want to calculate all of them because there's 10, but if I plug in 10, the last one, 10 times 2 is 20, plus 1 is 21. So if I want to add all these things up, yeah, I can go the whole thing, but since I know that it's arithmetic, I can come back to this list of equations here, take the sum of a finite arithmetic series, this equation right here, which I will rewrite for us. It is S sub n equals n times a sub 1 plus a sub n all over 2. Now, we are trying to find the sum of the first 10 terms. So S sub 10 is going to be 10 times. We know what the first term is. It was 3. We know what the last term is. It was 21. And we're going to divide that whole thing by 2. So 10 divided by 2 is 5. 3 and 21 is 24. 5 times 20 is 100. 5 times 4 is 20. So 120 is 120. And that is the sum of that arithmetic series. Okay, let's look at the last one for this. Again, we're adding up the first 6 terms. So let's calculate a couple of those. When I plug in 1, 1 minus 1 is 0. Any exponential expression to the 0 power, as long as this expression is not 0, is 1. 1 times 3 is 3. If I plug in 2, 2 minus 1 is 1. 1 half times 3 is 3 halves. If I plug in 2, 2 minus 1 is, excuse me, if I plug in 3, I've already did 1 and 2. If I plug in 3, 3 minus 1 is 2. 1 half squared is 1/4 times 3 is 3/4. And you can see that that will go on. Now this one, I don't have to find that last term, and I know that because this equation for the sum of an infinite geometric series ends up not needing the last term. And just as we're at it, I know that this is a geometric series because every time I go up, I multiply by the common ratio of 1/2. So I can use that S sub n equals a sub 1 times 1 minus r to the nth power all over 1 minus r. So technically we know everything that we need to know. We are summing the first 6 terms. So S sub 6 is going to equal a sub 1, the first term is 3, times 1 minus our common ratio we said was 1/2 to the nth power, which we know to be 6, all over 1 minus 1/2. And now we're going to go to our graphing calculator and we're going to type this in. So let's see here, parenthesis for the top to start, 3, parenthesis again, 1 minus parenthesis because we're going to put in a fraction, 1 divided by 2. Going to close that first set of parentheses. We're going to raise that to the 6th power. We're going to close that second set of parentheses, and then we're going to close the top. We're going to divide by. I can do 1 minus 1/2 in my head, and that's so it's just 0.5. And oh, I don't need that last parenthesis because I didn't open one, so let's delete that. And since I got a bunch of fractions in here, just to be safe, let's go 1 and hit fraction. That way we get a fractional answer. And it's 189 over 32 is my final solution. So this thing is 189 over 32. Now, because this common ratio is less than 1, we could potentially find the infinite sum of this thing. So if I go from 1 to infinity now and say 3 to the 2 or 1/2, oh come on Macaulay, let's make it neat. All right, so 1/2 to the n minus 1. Well, that equation, if you look back, is just S equals a sub 1 over 1 minus r. Well, that's easy. I already know what my first term is. It's the same equation, so the first term still has to be 3. And then 1 minus r is, it's still, my common ratio is still 1/2, so 1 minus 1/2 is 3 over a half, and when I divide by a fraction, 3 times 2 over 1, which is 6. Now the reason you can have an infinite sum if the common ratio is less than 1 is because notice this, if I go 189 divided by 32, the first 6 terms already takes up 1.5 of this 6. So each term, as we go first, the next term would be 3 over 64. The next term after that would be 3 over 128. So they get so small that each time you go up a term, you're adding almost an insignificant amount. All right, let's move on. The last part of what we're going to be talking about today is writing series in sigma notation. So your first thing you're going to want to do is you're going to try and figure out what type of series that it is. Is it going to be constant, arithmetic, or geometric? And those are the only ones that I have in the practice, but there are other types. Then we're going to find out what our first and last terms are because we may need that. We need to find out how many terms there are. We're going to need that for the upper and lower bound. And then we're going to find the equation for the sequence of terms. That's this list of equations right here. And then we're going to substitute, once we found all that, we'll substitute all of that known information into this general sigma notation. So let's do a couple of those. Fairly straightforward. If I look at this series, I'm trying to figure out what I'm doing here. And if you notice, if I go 1 to 3, that has a common ratio of 2. From 3 to 5, that has a common ratio of 2. So I look at this thing and I have a common ratio of 2. So to get each of these terms, I have a arithmetic sequence whose difference is 2. So what I'm going to do is I'm going to use that equation, and you can look back if you want, pause, but I know it. It's a sub n equals d times n minus 1 plus a sub 1. And we already know a sub n equals, the common ratio we said was 2. Get that? Was 2. I get n minus 1, and then my first term was 1. So 2n minus 2 plus 1 gives me an a sub n of 2n minus 1. This is my equation. This is my a sub I equation that I'm going to use in my sigma notation right there. Okay. Oops, got ahead of myself. All right, now, how many terms? Well, the way that I can figure that out, I need to know, remember, because my final answer here, I've got, and I can use whatever I want, and I'll just use n, equals 1, all the way up to I have to fill in the blank. So this is my a sub I equation, so I can already go 2n minus 1. This is my final equation. The only thing that I don't know is that last term. Well, this thing right here, that is my nth term. You know what? I've been using a lowercase n. I suppose I should do that. Nth term. All right, that is my nth term. So, if that's my nth term, if I plug 99 in for my nth term and say solve for n, well, now I know how many terms it would take to get me to 99. So I add 1 to both sides, and I get 100 equals 2n. N equals 50, and so this is my upper bound. So I'm just going to put 50 on top, and we're going to say that is it. There's our value. If I plug in all of the numbers from 1 to 50 into this equation, I will get that series. All right, looking at, here we go. This is the next one. Well, here, this one's going to be times 3, and then 3 to 9 is also going to be times 3, and then 9 to 27 is also times 3. So I know that this is a geometric series. And again, if I'm starting from my final, I'm going to go n equals 1. And I got to figure out how many times do I have to multiply by 3 to get to 59,049. Well, let's see here. I know it's a geometric series, and I have an equation, and again, go ahead and look back. Equation finds the nth term. This is the nth term. It figures out the nth term of a geometric series. Well, a sub n equals a sub 1 times r to the n minus 1. Well, if I fill in the blanks, I know that this equation would be a sub n equals 1, and I don't really need that 1, times 3 to the n minus 1, which I suppose I'll rewrite as just 3 to the n minus 1. This is my a sub I equation. So I can just plug that right in here. So I get 3 to the n minus 1, that works. Now I got to figure out what my upper bound is. Well, I can do that. I can plug in this expression. So I have 59049 equals 3 to the n minus 1. And I got to figure out what that is. Well, I am solving for a variable that is an exponent. And whenever you do that, you're going to use logarithms. So I'm going to take the ln of both sides. I suppose you could go multiply by 3 until you get there, but that might take a little longer. 59049, and then I bring this expression down, and I have n minus 1, this whole quantity times the ln of 3. And so n minus 1 equals the ln of 59049 all over the ln of 3. And then I'm going to add 1 to both sides, but I'll do that in the last step. All right, so this expression right here, I'm going to grab my calculator. I'm going to go ln 59049 divided by the ln of 3. And let's hope this comes out, the whole number is 10. So I've got this expression equals 10. So n minus 1 equals 10. Add 1 to both sides, and I get 11. So this is the sum of the first 11 terms in this particular series. Well, folks, I think that is all that I have. And as always, it has been a pleasure working with you this summer. I hope that you guys are not watching this on August 20th. You will be struggling if you get there. And just as a real quick Star Wars fun fact of the day, only one film franchise has made more money than the 6 Star Wars films, and that is the James Bond franchise. He had a bit of a head start though, because his started in the 1960s, and he has had only over 20 films. Well, as always, if you think I made an error, go ahead and give me a comment or send me an email, and I will try and get it fixed. And I hope you have a great rest of your summer. Goodbye.